to start with just reminding mostly some notation. Last time we defined a space of mesh laminations on our surface. So it's a lamination, so a closed subset of your surface that consists of pairwise, disjoint, simple, complete geodesics, together with these transverse measures. But if you want, you can just see it as limits of as simple curves with real weights on it. These are dense inside ML. And if I put so every simple multicurve is a measure lamination. If I put ML sub Z, it's the simple multicurves that have integer coefficients. And if we're given a train track, so a train track is just an embedded graph into our surface, such that we always assume it's trivalent, but it doesn't in general have to be. At every vertex, there's a smooth tangent line. The three half edges meet at a smooth tangent line. And we say that the train track is carried by it if you can homotope it into, like, first a small little neighborhood of it, and then you can just collapse it onto the actual train track. And so those are ML of tau. Tau is the train track, and the subset of MLZ that's carried by them is MLZ tau. And then given a train track, you can put weights on the edges, so it's positive real numbers. And we say that a set of weights satisfy the switch equations if at every vertex it satisfies that the weight in the incoming is the same as the sum of the two outcoming. And the solution set to the weight equations is W tau, and the integer solutions WZ of tau. So in general, again, you have to, for every vertex, you get an equation like this, and they have to be simultaneously satisfied for it to be a solution set. So you get, in general, V number of vertices equations, in E number of edges unknowns. Okay, and what I ended with yesterday is the following fact, which I will give you an idea of why it's true, that we have a one-to-one correspondence between the measure laminations carried by tau and the solution set tau, and the same with the integer points. So let me give you an idea why this is true. So let's first suppose we're given, so tau is some fixed train track, we're given a lamination that's carried by tau. Okay, so we have tau, train track. And we want to get the solution to the switch equations. So that is carried by tau means that I can homotope it into some neighborhood here. So the entire lamination, which might be a multicurve, or in general will not be, lies in here. And I can then get weights on the corresponding train track by just taking the, let's see what Paul will show, the transverse measure to take small arcs that only intersect the corresponding edge and not any other edges. So this is like I, this is edge E. The weight assigned to edge E is just the transverse measure that lambda assigns to that arc. And just by definition, being a transverse measure, that these are homotopic, invariant under homotopy transverse to relative to the train track, is going to satisfy the switch equations. So this WE defined this way is in the switch equations. And so if this is a multicurve, then what happens is just that here is more like it looks. There's finitely many strands in each one. And this measure here is just the intersection of the multicurve with that edge. So the weight assigned to edge E is this, which will be an integer. Is that okay? So here is just the number of strands you have of your curve here. This is an integer. Okay. Going the other way, so given a solution to the switch equation, let's first suppose we're given a solution in here. So WE. So where they're all integers. So if I look at one vertex, we have like A, B, C, where A, B, and C are all integers. Well, then you just, so I guess I kind of did this last time, but say it's maybe 5, 3, and 2. You just put wherever you see a 5, you put 5 strands, 3 strands parallel to that edge, 2 strands parallel to that edge. And since you know that you're not allowed to create any crossings, there's a unique way of connecting this. You have no choice but to connect them like this. So for example, on the torus, and say we have this train track. So these are supposed to be the same point here, and this is supposed to be the same point, and I want to go like this. So maybe, maybe let me do the same numbers. So maybe this edge here has weight 2, this edge has weight 3, and then that has to have weight 5. So the corresponding simple multicurve, or in this case simple curve, or in general simple weighted curve, would be so you put 2 here, 3 here, and I mean now it's fine. You're just going to connect these the only way you want, but if you want, only way you can, but technically it would be 5 here. 1, 2, 3, 4, 5, and then you connect them. So like this. And you'll get a simple curve. Since these always match up here, these always match up here, it's going to connect. It might not be, so in this case, it is going to be one connected curve. In general, it could be maybe, so if I put, maybe if I doubled each number here, I would just get twice this curve. So technically what I would get is a non-primitive curve, but we will instead think of that as this primitive curve with weight 2. Okay. So this does give you a simple multicurve. So if we have this gives you something in MLC in general. Okay, but what if we have general weights? Well, let's first think, suppose we have rational weights. So what if, so I guess I didn't give this notation, but here I just mean solutions. So maybe I'll not introduce. So we have with each weight being a rational number. Well, we can do a very similar thing. We have finitely many edges, finitely many weights. I can take the common denominator, multiply through with it, and then what I'm left with is something in here, which gives me a simple multicurve, and then I have to divide by that common denominator that I multiply through with. So just to do a concrete example in the torus, suppose I had maybe, okay, let me draw one of these first. So sorry, there's always a puncture here somewhere. Maybe I should puncture is across, and these ones are the edges. It's like this. So suppose I had maybe 1/2 and 2/3. So meaning this is also 1/2, 2/3. And I get 7/6. The sum of those two. Okay, so if I can think of this as if I'm common denominator 6, if I multiply everything by 6, I will get 3, 2, and 7. So this is also 2, and that's also 3. But what I have to divide that by 1/6 for it to be the same. So this thing here gives me multi-curve. No, wait, something is wrong. That should be 5. If this should be 4. Thank you. Good. Thanks. Okay, so it's not the same as this, but I mean, you can do the same. You can put 4 strands here, 3 strands here, and so on, and you're going to get a simple multi-curve here, or again, we're going to get just a connected simple curve here, and then the results in so this gives you, like the 3,4 here gives you some simple curve, and then what these weights, 1/2, 2/3 give you is then 1/6, like that simple curve with a weight 1/6. All right. So the harder thing, which I'm not going to prove, is like what happens if, well, let me give you an idea, if we just have a general solution. These are just some real numbers. Well, they can't be negative, but plus they're real numbers. Well, what you do then is you take thickening.
Excuse me.
Yes.
Before you go there,
Yeah.
what happens if you want to do, for example, if I have 2, 2, 4, do I cancel out some?
Sorry, if you have one.
2, 2, 4.
2, 2, 4.
Yeah.
Yeah.
That should be like the same as 1, 1.
Yeah, yeah. So what happens if we do 2? Yeah, exactly. So if we have 2 on both, so we have 2 here, 2 here, 2 here, 2 here. Well, what you get is, so then you have a 0 here, right? If so if you have, no, sorry, you have a 4 there. Yeah, so 1, 2, 3, 4. So you have to do, you do this, yeah, sorry. It's this, yeah, I see what you mean. It's the same as the 1, 1, but double. Yeah, so if you go here, yeah, what happens here? So what curve is this? Maybe I'll draw it a bit less ugly. So the curve would just be, no, why can't I do it when I have that? Yeah, no, it's fine. Okay, so what is this curve? If I follow it around, I start here, I come to here, I come to here, and I come to here. I'm back at where I started, but then I do the other one. I go from here, I get to here, and I'm back to where I started. So it is, this time it's like a non-primitive. It's the same curve as 1, 1, but I go over it twice. But I do have identification of, I think of that instead as a weighted curve. So I take 2. So like the 2, 2 is the same curve as you get from 1, 1, but with weight 2. So that's why I think of it as a multi-curve, because it has a weight. But it's true, yeah. So I do some identification between non-primitive and primitive with weight. Okay. Yeah, sure. And in fact, Wallace, this is the same as you just did. Take a rational slope and project it to your torus. This 2 and 2 or 2 and 3 comes from the rational slope. So you could have you can see from there, so you don't really need this weight. You just need to know these two numbers, and there's a unique way up to, do I go this way or do I go that way? Right, like was my slope 2 over 3 or minus 2 over 3 or 3 over 2, whichever is the right one here. So that's why I also need to know, is it on this train track or the other train track? But knowing whether it goes this way or that way together with those two numbers tells you which one it is. Any other questions before I move on? Okay, so if we now have just any non-negative weights on it, what you do, you take a thickening, like take a close thickening of your train track. So here I'm going to be very hand-wavy, but so locally it looks like this around the vertex. So technically what you can do is, take a band complex where you replace each one of the edges by closed bands, but let's just think of it as a thickening. And then just foliate this closed set by geodesics. Okay, so that gives you lamination, but we want a transverse measure on it. So I need to say for every arc transverse to this lamination that I get here. So lamination is now inside there. I don't know what colors to use, but okay. So I'm assuming now this is actually, there's not finitely many, it's an actual lamination, that's not the curve. And so I'm given weights too. So for each edge I have like a weight. I have like an A and a B and a C. A, B, and C are positive real numbers. So what is clear is that if I take this arc that's transverse to my lamination, I can just, so if this is I can define the measure lambda I of I to be the weight A. And the same for all of them. All right, so the weights, the given weights give me measures to every arc that's of this form. However, it doesn't tell me what should I assign to this little arc in there. But it's a theorem due to Thurston that the weights on tau uniquely determine a transverse measure. Yes?
The train track, the arcs in the train track, they're not geodesics, are they?
These, the edges?
Yeah.
Yeah, they're not geodesic.
They're not geodesic.
No.
So how do you complete it? Get like,
So this is, so yeah, what do you mean, complete the picture?
no, it's when they separate. I mean, if you take a geodesic, for example, if the left curve is close to a geodesic, if you take a true geodesic near it, then it will just cross, right?
It will cross.
How do you complete the thickening with geodesics?
How I foliate this set with geodesics?
Yeah.
I mean, so inside it, so locally it just looks like, so inside I just have this, and this I foliate by geodesics. I mean, if you want, you can do it just topologically and then straighten it in your metric. So,
Okay, you take any curve that goes around and then you like shorten it so it becomes a geodesic.
I mean, yeah, so. Yeah, I'm not sure now what. I mean, one thing you can always do, but I don't think you need it here. But what one can do, one can always make your train track as geodesic as you want. So getting the geodesic or the curvature to be as close to zero as you want by doing what's called splitting. So one can, so one can take any train track and make it like more and more geodesic by splitting or collapsing certain vertices. So one can assume that it's as close to geodesic as you want. Maybe that is needed for this argument, but I didn't think it was. Yeah. So maybe I'm being a bit too quick because So you can be carried by train track and you can be strongly carried by train track. Strongly carried by train track really means that you can put your lamination in a small like in your actual geodesics inside a small neighborhood of the train track. Sorry, so yeah, so maybe I'm. So what is the assumption here? We have, yeah, we don't have our lamination yet. We just have weights on the train track. Yeah, so let's assume, so take it as a fact, sorry, that you can, yeah, that your train track is very close to being geodesic. So all these edges are very long and are very small curvature. And then, yeah, maybe that's necessary for this to also make sense. And then everything parallel to this will be very close to geodesic. So then when you take the actual geodesic, you should be close, Hausdorff close to this, and should lie inside that neighborhood. Yeah, sorry. So there is more, okay, one should be more careful than I am here. But if we pretend that this works, and then it's a theorem by Thurston that given a train track with weights, there's a unique transverse measure on that corresponding lamination that's carried by it that they determine. So on L is this foliation of a closed neighborhood. Okay, but really, yeah, sorry. So I said that multi-curves, if you allow any weights, well, let's say weights in the rationals, are dense inside measure laminations. So you can see that also in this way, that if you have any real weights here, you can approximate them by rationals. And every rational gives you a rational simple multi-curve, and those multi-curves will converge to that. Okay. Yeah, so maybe that's the way to take a sequence of rational numbers that converge to these real numbers. Each one gives you a closed curve that you can pull tight and take a limit like that. Okay. Okay, but the goal with this, yeah, so let's say the most important thing is that the thing, if we have a measure lamination, which may or may not be a curve, it gives you weights on a train track, and if you have solutions that are either integer or more generally rational, it gives you a multi-curve. Okay. And the goal with this, the reason why I'm talking about this is because this is going to help us define a natural measure on the space of measure laminations, which is the generalization of a Lebesgue measure, or viewed in charts, is a Lebesgue measure. So let me say how one does that. So first some facts, most of which are not hard to prove, that every measure lamination is carried by some train track. Okay. And determines, by what we just say, a unique solution. So a unique point in the solution set of tau, where tau, some train track tau. Right? It's just, so it's not this argument, it's the first argument, that you can just take some very small neighborhood of lambda and collapse it into a train track. And there you can also, so depending on how small you make your epsilon neighborhood, the more and more geodesic your train track will be as well. Right, the closer it follows to it. Okay. There are only finitely many train tracks needed to carry all measure laminations. Okay, so this is, can be done either by compactness argument. So ML of S is not compact, but if we projectivize, it's locally compact, and we projectivize it, so divide quotient out by R plus, or look at the set of laminations, so support, that is a compact set. And being carried by train track is a local property, because it's about being homotop into it. So you can use a compactness argument to say there's finitely many, but one can actually also draw them all. One can take a pair of pans decomposition if you're used to hyperbolic surfaces, and inside each pair of pans, there's finitely many things that can happen where you can't intersect them things. You can actually draw all of them in there, and then you connect the pair of pans with cylinders, and you can draw all possible things you need to do in the cylinder. So this can be done very explicitly. You can write them all down. Okay. But from this, it follows that we can write ML of S as, well, those measure laminations carried in by tau 1, those measure laminations carried by tau 2, those measure laminations carried by tau n. So it's a union of these, and each one of these can be identified with the solution set to the corresponding train track. We know that ML of tau is, we can identify it with the corresponding solutions to the switch equations. And it turns out that this, well, it's also not hard to show. So E is a number of edges of a train track, V is number of vertices, that this can be identified, or I guess with a positive quadrant in this space. Because when we said we have V equations in E unknowns, so as long as these are linear independent, this is the size of a solution set. And so just under some very mild conditions on the train tracks. I don't want to go too much into it, but for those of you that might know some about train tracks, I think the only thing you need to assume is that it was called recurrent, that, so yeah, maybe I'll come back to it, that you have a train track that has a solution where everything has a positive weight. There are some train tracks where you can't have a solution without putting 0 somewhere. And that is a highly non-generic situation. Or maybe I can draw an easy one, actually. So suppose if I'm doing this right. And so this is a train track on some surface. So this, maybe I should have drawn the train track in a different color. This is a train track with 2 vertices and 3 edges. But if I put weights A, B, and C, the only solutions to satisfying here, you have to have the B plus C is A, and A plus C has to be B, C has to be 0. So even though this is a train track, it's not a recurrent train track, because you can't actually have a path that goes over all of them. But I think up to that conditions, these are going to be linear independent, or you're going to get the full solution set. Okay? And I leave it as an exercise that let's do it on for the exercise, let's suppose S is closed. That E minus V is always less than or equal to 6G minus 6, where G is the genus of a surface, and it equals this if and only if tau is maximal, which in this situation we're closed, so closed with genus at least 2, because it's hyperbolic, just means that all complementary regions are as small as possible. Remember, we're not allowed monogons or bigons, so as small as possible means that all complementary regions are triangles. Okay? So this is just the Euler characteristic area argument to compute that this. So, and here I'm using this trivalent, so there's 3/2 or 2/3 of as many edges as vertices. And then you can use that, and that the area of these are pi, and so on. Okay. So I have those two facts. One more that I need to get the conclusion is that, and this is maybe less obvious, but I can explain it in the train track or in the tours, for example. Maybe I should say one thing before I do a third fact, that the reason why I said closed here, if I didn't say closed, so if I have punctures, then I also allow puncture monogons, because those are also the smallest possible kind of things. And either that you're not the puncture torus, or if you puncture torus, you also want this recurrence condition. Because if you notice these train tracks, there's a puncture. The complementary region is a punctured bigone, which is kind of bigger than the smallest you're allowed to have. Could have triangles and punctured one-gons. And I could extend this to break this into having, instead of a punctured two-gon, so with two corners, I could break it into a three-gon, a triangle, and a punctured monogon, but that will never be recurrent. You won't be able to find a solution that all have non-zero things. So that's why, so the maximal train tracks in the torus are these two. That's why I kept drawing those. So the third fact that we need is that, so I said we have this finite collection of train tracks that every mesh lamination is carried by at least one of them. It could be that you're carried by more than one, but the dimension of such things is strictly less than 16 minus 6. Strictly less than 60 minutes. Okay. So this is not so obvious, but if we look at the torus, and we have these two train tracks, I keep drawing, this one, and the other one that I always have a harder time drawing. To adjust. So there's a puncture here somewhere. This one should lean the other way. This way. So suppose this is tau 1 and this is tau 2. What is, or let's say even just curve, not mesh lamination, what is a simple curve that's carried by both of these train tracks? Can anyone see if there's any curves that lie in both of these? If you think of like this one here leaning this way, that should be like a projection of rational slope lines going this way, and this should be rational slope general going this way. What could be carried by both? Is there anything that could be carried by both? Yeah, I see some people making the movement. If you have this line, right, or if you have this line, they will carry by both. But only that. So it's only ones that have like either 0 on this one or 0 on that one. So instead of getting the full R2, you just get an R. So you get a lower dimensional thing. And in general, if you have two train tracks, we're going to assume they're all maximal. So if you carry it by 2, and they're actually distinct train tracks, then there must be some edges that they didn't go across. Can go across all edges on both. So just like some can only be homotopy to some common ones, so it's going to have a lower solution set. Okay. So this is true in general. So what we get from this, the conclusion, if you believe these arguments, is that so ML of S, which we wrote as a union of these finitely many train tracks, the ones carried on finitely many, I can only take the ones that are I can ignore all that are carried by 2 train tracks, and just I can view it as a disjoint union of this. And each one of these, if I assume they're all maximal, so if you're not maximal, I'm going to care about stuff up to L to the 60 minus 6, because that's how I want to count. It's going to be the dimension of this. So I can ignore everything of lower dimensions. I can ignore things that are not carried by maximal ones. I can ignore things that are carried by more than one. So I can take the disjoint union of this. And each one of these is the solution set to each one. And each one of these is of dimension r to the 60 minus 6, or plus 2r if we have punctures. So in particular, which is a lesser important part of what I'm saying now, but this is homeomorphic to r to the 60 minus 6, or plus 2r. Puncture, r is the number of punctures. But thinking of it that way, yeah, because, sorry, so each one of these, so maybe. So I have these charts of ML given by the finitely number of train tracks. Okay. So I'm going to use this to define the Thurston measure. So the Thurston measure on ML is the following limit, and I'm going to explain to you why this limit exists. Okay, let me say plus 2r. I'm going to sum over all measure lamination, of all integral multicurves. Yes, maybe I should. In S. So this is a measure on ML. This is the usual Dirac measure centered at, so this I'm just summing over simple multicurves with integral coefficients. I scale each one by 1 over L, and I scale the entire sum by L to the dimension of a space, and take the limit as L goes to infinity. Okay? So this is what it is by definition, but this limit better exists for this to make sense. So why does it exist? So first off, it's a finite sum. So maybe I should have written ML Z of S is the union of ML Z of these tau i's, some finite union. So I can break this into, and I think of it as a disjoint union, into a finite sum where each time I sum over here. This is why here I can ignore the ones carried by more than 1 because they're going to disappear compared to this, what I'm dividing out by. So this measure here is a finite sum of things of a form L to the right dimension. I just now look at the ones, say, carried by tau 1, and do the same thing. But this, under identification of simple multicurves carried by this tau and the integer solutions to the switch equations, I can write this as, say, solutions to integer solutions to the corresponding switch equations. But I can identify this with, or at least a positive quadrant, something in, so integer points Z to the 60 minus 6 plus 2r 1 over LP. Where I now think this last one, I think of it as a measure on R to this power, right? Just by that identification. And now it's exactly like what we did for the torus. This is the Lebesgue measure. We did this for 16 minus 6 plus 2R equal 2, but this is true in general. So what is this? So I think of this now as a measure on R to just Euclidean, oops, I shouldn't do that, 16 minus 6 plus 2R. So again, if L was 1, it was really just, it's supported on all the integer points, the integer lattice in R to this dimension. But now I scale that lattice by 1 over L. And so eventually, like as L gets bigger, this gets more and more dense. And it's like as if it's in the limit supported on every real number, and then dividing by the dimension of a space. So this is a Lebesgue measure in the limit. So this thing here goes to the Lebesgue measure on R to the 16 minus 6. So this is why the limit exists. Now it's just a finite sum of such measures. And so really what you should think about the Lebesgue measure, the Thurston measure on ML, is really like under these identifications, so you have charts into R to the 16 minus 6 given by train tracks, by finitely many charts, and restricted to each one of these, so restricted to the set of measure laminations carried by one of these, it really is just the Lebesgue measure on the solution set of it. Okay. It's okay? An important theorem that's going to come up tomorrow is that, as this is by Maser, I think from 85, definitely from the 80s, is that, well, first off, the Thurston measure is mapping class group invariant. From the way we define it, that's clear, so it's not really it's not the statement of the theorem, but let me just convince you why it's true. So if we define it as this limit, ML Z of S is mapping class group invariant. If you take a simple multicurve with integral coefficients, act by mapping class, you're still going to be a simple multicurve. So from the way we define it, you can define a Thurston measure in other ways. When some other ways it's not so obvious as mapping class group invariant, but it is, from the way we define it, it is. What is important, or what the content of the theorem is, that it's ergodic. So with respect to the action. Okay. We're not going to need this now, but tomorrow, when we come back to Mirzakhani's theorem, this is an important theorem. We're going to kind of use this as a black box. But besides this, this is a very important a theorem that goes into the proof for Mirzakhani's theorem, both in the original proof by Mirzakhani and by what I did with Juan Soto. But besides this theorem, the way Juan and I prove it is very combinatorial in nature. We use this kind of as a black box, but besides that, the rest is very combinatorial, using train tracks, in fact. I have how many? 5 more minutes? OK. So I want to just introduce one more space. I should at least have time to define it today, and then we continue tomorrow, and then we're going to return to counting, to Mirzakhani's curve counting theorem. But a generalization of space of measure laminations is a space of geodesic currents. So which I'm usually just going to refer to as currents, even though I know currents also has other meanings in, when it comes to measures. From now on, I want S to be closed. So it's a surface with genus at least 2 and no punctures. Most of the things I say would be true also with punctures, but there's some care you have to take in certain areas that I don't want to. So let's assume it's closed. I'm going to let G of S tilde be the set of all geodesics in the universal cover of S, so all the geodesics in the hyperbolic plane, okay, unoriented. Which I can identify with H2. So what is that? So if I think of, let me draw H2 in the disk model instead of upper half plane. So any geodesic here is determined by its two endpoints. Right? Drawing them very well, but the geodesics here are either diameters or half circles that are orthogonal to the boundary. So given 2 points on the boundary, which we can identify with a circle, S1, the A and B determines a unique geodesic. So I can think of this as the circle cos itself minus the diagonal, because I can't take A, right? They have to be distinct points. And since I want unoriented, A comma B will be the same as B comma A. So let me also quotient out by this, where A comma B is B comma A. Okay? So it's just a set of all geodesics, unoriented. But now a geodesic current, and again, I'm doing this thing where S is really topological surface. I talk about geodesics. Technically, what we do is put, when I identify this isometric to H2, I think I put the hyperbolic metric on it, define it using that hyperbolic metric. But it turns out that up to homomorphism, this space doesn't depend on a hyperbolic metric. That's why I write it as a topological space. But a geodesic current is now a measure on this set that's invariant under the pi1 action. Okay. So geodesic current is pi1 invariant radon measure on this space. Radon measure, I just mean that it's locally finite. It's an infinite measure in general, but it's locally finite. So a finite on compact set, and also I guess an inner regular and outer regular, so some niceness condition. But the main point is that it's locally. Okay. So that's what a current is. Let me, in 1 minute, just give you an example, so it makes it a little bit less mysterious. So it turns out that both any curve, any closed geodesic on your surface is a current, or can be identified with a current. So any, or multi-curve if you want. So in this case, it's simple or not. So it doesn't have to be simple. Is a current. We're going to identify with a current the following way. So if gamma is your curve, take a set of lifts. So gamma is maybe, so a set of lifts. Gamma tilde to the universal cover. So you have these, they might intersect if it wasn't a simple one. And then I want to define a measure on the set of all geodesics, or on the set of this double boundary, S1 cross S1. So it's enough if I define it for two small open A and B. Maybe I take these. So I want to define a measure. So this gamma is going to define a measure, F sub gamma. And I'm just going to define it as the measure it assigns to A cross B is just the number of lifts on my curve with one endpoint in alpha and the other one in A and the other in B. So it's a counting measure. So in this case, the way I drew it, it's 2. These ones land in here. This one starts in B but lands outside A, so I don't count it. So it's really just a counting measure. And we will, instead of writing this, we will identify, I will just call it gamma. So the curve I will now view as actual current. Okay, so I'm out of time, but next time I start, also the space of measured laminations will also be in curves. So maybe I'll write this just for start tomorrow. So all curves or multi-curves is a set of currents, and we will see that in fact ML of S can also be identified with a subset of currents. And in fact, Teichmüller space, so the space of all hyperbolic metric that you can put on it, can also be identified with a subspace of currents. So this is why currents are important to us. They unify all these three things as points in the same space, and it makes it easy. And in fact, there's many classes of metrics that you can embed into a space of currents. And so I will start with that tomorrow morning.